Okay, guys, good morning or afternoon. Today, lesson 6, we're going to be talking about how to find the end behavior of rational functions. Why do we do this? Because it helps with graphing. So if you need to pause the video here to copy down your intro, go ahead. Take about, no more than about a minute for that. But other than that, we'll go and get started. So let's go ahead and take a look at some graphs of rational expressions to kind of see what we mean by end behavior of rational expressions. So here's a graph of a rational expression. Now, you're going to notice that a couple of these graphs that we're looking at today, probably all of them actually, are going to look a little bit different from the ones that we're used to seeing so far, because rational expressions can look different in a few ways. But let's talk about what I mean by end behavior. In case you guys forgot what that means, end behavior means what's happening to our graph at the end of the function here. So the way we talked about that was this limit notation. I want to find the limit of this function as I go to the right forever. And that means what y value am I approaching as I do that? Well, as I go to the right, let's see what y value I'm approaching. Well, as you guys can tell, it looks like this line is getting really, really flat. There's a horizontal line there. It's kind of hard to tell with the poor image that we have up here on the screen right now. But let me clear off my writing and we'll zoom in a little bit. It looks to me like it's approaching an asymptote like right about here at about x equals 1. So it's approaching a y value of -1. In other words, it's just the horizontal asymptote of the function at that point. And as you guys can see, the same thing is on the left side. On the left side, as I move to the left forever, it's approaching the same horizontal asymptote, which is approximately a y value of 1. So I can go ahead and draw the horizontal asymptote on there, and you guys can kind of see what I'm talking about. There it is. So it's y equals 1 is that horizontal asymptote, and that's the blue line that the function is approaching as I move to the left and right and left forever. So I didn't write the limit to the left, but the way that you would write that is that the limit as x approaches -infinity of my function is also 1. Okay, so that's what we mean by end behavior. What's happening at the ends of this function? In other words, what's happening at the far left and far right of the function? It's approaching a y value of 1. Okay, so let's take a look at another one. Here's another one. You guys can see it. These do look pretty weird, but here's another one. So what's happening here at the far right of my function? In other words, what's the end behavior of this function? And what's happening at the far left of this function? Well, either way you want to cut it, it seems like there is a horizontal asymptote right about here, right? So as I move to the right forever, my y value is getting closer and closer to a y value right about here, which I can see. I'm not sure if you guys will see it, but it's a y value of about 2. Okay. And as I move to the left forever, that's what it means to go to -infinity. My y value is approaching the same dotted line at a y value of 2. So the end behavior is 2 because as I move to the right and left, I'm approaching a y value of 2. Let's take a look at another one here. All right, so looking at this function, how would you guys describe the end behavior? As I move to the left forever, as I move to the right forever, what y value am I approaching? It's 0. So the limit of this function as x goes to infinity is 0. And the same thing is happening on the left. As I approach -infinity, we're approaching the x-axis, which is a horizontal asymptote of y equals 0. So there's that. Let's take a look at one more. Okay, so this one is also a little different. This is also a rational expression. But what is the limit of this thing as x goes to positive infinity? In other words, what y value am I approaching as I move to the right? Well, as you can see, this time it just keeps going up. It's not getting flatter and flatter up against some invisible horizontal asymptote. It just keeps going up. In this case, the end behavior is infinity. The y value just keeps going up and up. How would you guys describe this one? What's the end behavior at negative infinity? In other words, what y value am I approaching as I move to the left forever? Well, here's to the left, so I'm going to keep going. What do you guys see is happening there? Well, I don't see it getting flatter and flatter. It seems to be getting further down. It just keeps going down, 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 down. So what would we say that is? That would mean that the limit as x approaches negative infinity is negative infinity. So that's what we mean by the end behavior of rational functions. End behavior is something you need to know about and what it looks like and how to find it if you're going to be graphing rational expressions, which is exactly what we're going to be doing today. So before I do that, though, I want to review a couple of things with you guys. First of all, a little while back, we graphed a certain kind of function. I don't know if you guys remember this one, but remember 1 over x? 1 over x looks like this. And as you guys can see, the end behavior is 0. So as x goes to infinity, y equals 0. And that's on both sides. And if I were to change this to a power of 2 on the bottom instead, the shape changes, right? We remember this from last Friday, but notice that the end behavior is still the same. As I go to the right, it's still getting flat up against this x-axis, which is aligned y equals 0. So for any function, any rational function of the form 1 over x to the n, the limit is going to be 0. So here's we're going to be making a chart, and this chart's going to have 3 columns on it. Maybe we'll do 3 rows. I think it'll be easier that way. Let's do 3 rows. So we'll title this End Behavior of Rational Expressions. So what we just talked about, demonstrating that to you on the graph, was that when you have a function of the form 1 over x to a power, matter of fact, it doesn't have to be 1, it could be any number on the top. But anytime you have a function where it's a over x to some power, it doesn't matter whether you're going to the right or left. In other words, it doesn't matter whether it's positive or negative infinity. The limit's 0. The function just gets closer and closer to y equals 0. And so that's our limit at the ends there. So that's case number 1, okay? We'll call that case 1. Now let's talk about case 2. For case number 2, let's look at another graph. What if I just put a number in here like 5? It's interesting. Y equals 5. There's my function y equals 5, right? Well, look at this thing. How would you guys describe that doesn't even look right. How could that be y equals 5? Let me back up a little bit. Something's not right. Oh, it says y equals 4. Okay, that looks right because it wasn't at 5. It was at 4. Okay, so how would we describe the end behavior of this function? You know, what would you say is happening? What is the limit of this function as x goes to infinity? Well, as I go to the right, what do you notice? The y value. Does it ever change? It's a flat line. It's always staying at 4. So when you have a flat line, the limit is going to be 4 as x goes to infinity. In fact, it's the same thing for positive and negative infinity. So it doesn't really matter whether it's positive infinity or negative infinity. Since my function is just a constant number, the limit of 4 as x approaches infinity or negative infinity is just 4. Okay? So that's our second case that I want you guys to be aware of. is that the limit as x approaches positive or negative infinity, if you have just a number there, we'll call it a, then that's what your limit's going to be. Now, in both of these cases, those were horizontal asymptotes. In this case, we had a horizontal asymptote at y equals 0. And in this case, we had, you can call it, I'm going to say horizontal asymptote, even though that's not really an asymptote on the last slide, but for the problems that we're going to be doing today, when you have this situation, that's what your asymptote is going to be. So, in the case where you try to find the limit of just a number and it's just a, that's going to tell you where your horizontal asymptote is at. So in both of those cases, you have horizontal asymptotes. For this one, the horizontal asymptote is at 0, and that's what the end behavior is. And for case 2, the horizontal asymptote will be at a, and that is your end behavior. Let's go ahead and take a look at a final case. Our final case is, what about when we have well, I don't want to put, on this one actually we don't want to put plus and minus because actually they're different on this one. So let's do positive infinity and we'll do negative infinity. What about whenever we still have an a, all the problems had an a, on the first one though it had an x on the bottom, and on the second one there was no x. But for this one, what if the x is on the top with the a like that? Okay, what's our end behavior then? Well, I don't know if you guys realize that's just a polynomial. Okay, and a little while back I gave you guys a chart about polynomial end behavior, and it looked something like this. It depended on whether a was positive or negative. It also depended on whether the n was even or odd. Okay, when n was even and we had a positive a, the graph went up on both sides. So the limit at the right was infinity, and the limit at the left was also infinity. But when n was even and a was negative, it went down on both sides, in which case the limit on both sides was negative infinity. But when n was odd and a was positive, it went up on the right and down on the left. And that meant that it was positive on the right and negative infinity on the left. But when a was negative, it reversed it, so it looked like this. Positive infinity on the left, negative infinity on the right. Okay? So that's how we're going to know what our end behavior is for our rational expressions today. It's a little something you're going to want to remember, is all those kinds of things. Okay, so keep those in mind for the lesson. You might be feeling a little confused right now, but what you guys just wrote down, make sure you have really good notes here. So if you need to ask the sub to pause, make sure you get really good notes, because this is your master key for the day. This is going to be how you answer every question for the day. Okay? All right, so we're going to go ahead and move on. Now, once again, I still have one more thing I want to review with you guys before we actually jump into the problems for the day. Do you guys remember when we talked about, you don't need to write this, but do you remember how when we talked about polynomial functions, like this one for instance, do you remember which term depended or determined the end behavior? It was the one with the biggest power. So for instance, on this particular polynomial, 5x squared is what determines the power. Now since my a is positive and my n is even, looking back at our chart, that means it goes up on both ends. And when that happens, the limit as x approaches negative infinity of our function would be infinity, and the limit as x approaches positive infinity, as we go to the right, oops, I guess I should put y there, sorry about that, is also infinity. Okay? If you guys want to practice one of these really quick using the chart that you copied, I'll give you one more. Consider this polynomial. I'll give you a second to try it out. See if you guys can determine the end behavior. I would like you guys to draw the arrows, and then I would also like you guys to be able to fill in these blanks. Now this is just review. We've done this already this year. Just giving you guys a chance to get your bearings. So give it a shot, pause the video. Don't take any more than a minute. You know, try it for 30 seconds, check your work with a neighbor, and then unpause the video and you can check your work. So the term you want to look at is this one. Since I have a negative a value and an odd power, it goes up on the left, down on the right. So up on the left means that my left-handed limit is positive infinity. And since it goes down on the right side, my right-handed limit is going to be positive infinity. So that's your end behavior of polynomials. Okay? So now today we're going to be looking at rational functions. All right, so we're going to talk about how do you find the end behavior of a rational function. So this is going to be example 1. So let's go ahead and call this example 1, and we'll call it A because I'm going to do quite a few with you guys. Go ahead and copy down the equation. Now you don't need to copy the graph. You can if you want to, but it's not the main point for the day. Okay, but go ahead and write down the equation. All right. If you need to pause the video, go ahead, but I'm going to go ahead and continue with this. All right, so now a rational expression is when you have one polynomial over another polynomial. Now we know that the end behavior for the top polynomial would be determined by this guy, and we know that the end behavior for the bottom polynomial would be determined by this guy. So here's the situation. If I want to find the end behavior of this function, so I'm just going to put f of x, because that's what this function is called. I want to write that whole thing, so I'm just going to put f of x. If I want to find the end behavior for that function, then that's basically going to be the same thing as the limit of just these two, because really it's these two that are determining what happens. So I don't really need to include the other numbers. They don't really determine the end behavior. It's the first numbers that do. Right? So here's the first thing you do. You're going to start by stating that the limit of your function is equal to the limit of its first two terms there on the top and bottom at infinity there, because they're going to be the same thing. And then what we're going to do is we're going to reduce that fraction if possible. So how can I reduce this? What's negative 3x squared over x squared? Well, that's just negative 3, right? Okay, because these cancel, correct? Well, now we get to go back to our little chart we had earlier. Which case do I have in this particular instance? Am I taking the limit of a number over x? Am I taking the limit of a number, or am I taking the limit of a number times x? Well, I'm taking the limit of a number. And what is the limit of a number at infinity? We said the limit of any number at infinity is just that number. So the answer for this is negative 3. Okay? Now, so let's slow down here and make sure we've got the process. The first thing you're going to do is you're going to state, okay, what's the limit of my function at infinity? Then you're going to say that's equal to the limit of just those first two terms at infinity. Then you're going to reduce, and then you're going to use that little chart that I gave you guys earlier to figure out what's the limit of what you're looking at. But that's the process you go through. But now let's actually interpret it. Okay? What that means is that as my function moves to the right, it's approaching a y value of negative 3. And what that means is as I go to the right, I have a horizontal asymptote at negative 3. Now, you could do the same thing for what happens to the left. the limit at the left of my function is still going to be the limit to the left of just those first two terms, which still reduces to just -3. And on our chart, we saw that it didn't matter whether this sign was positive or negative, whether the infinity was positive or negative, it was still -3. So that means at the left, the limit's also -3. So I don't know what's happening. Somehow the function could go like this, it could go like this. We don't really know what the shape of the graph is, but all I know is that there's a horizontal asymptote. You might want to write that. Horizontal asymptote at y equals -3. Okay? Now, I'm going to show you what the graph of this function up here actually looks like. So if we were to graph this weird-looking function, what would it look like? Let's see. Display my answers here. There it is. So now as you guys can see that on the right side of the graph, my line is approaching my green line there of -3, and it's also approaching the same green line of -3 over here. So at both ends, it's approaching that dotted line that I had of -3. So there it is. So let me review with you guys a little bit before we go any further. Okay. Cover up the answers real quick so it's not ugly. So we write this. That's what we're trying to find. We only look at the first two terms. We reduce and we use our chart to find the answer. And whether you're looking at case 1 or case 2 on this slide, that's where you're going to have a horizontal asymptote. These ones don't have. The last one, case 3, does not have a horizontal asymptote. So our horizontal asymptote is what the end behavior is, which is -3. Now, just so you guys know, for case 1 and for case 2, you really don't need to write opposite limits for the positive infinity and the negative infinity because it does the same thing at the left and the right. Okay, so I want to give you guys another one that's going to be a little bit like this. So here we go. Pick one that's kind of similar. There, I just passed a good one up. There you go. All right, so I'd like you guys to try this problem. Okay, see if you can find the end behavior. Take about, probably need about 2 to 3 minutes. Then unpause the video, see if you got the right answer. And we'll try one more practice like that before we move on to the next. Okay, so the answer is basically 2. Okay? Why? So the limit of our function is just the limit of the first two terms at infinity, which reduces to 2. And the limit of a number at infinity is just that number, so it's 2. Okay, same thing for the negative infinity. It's no different, and so you really don't need to start by writing both. You could really just put plus and minus infinity here and not write the whole thing twice. But it would be nice if you guys do state where the horizontal asymptote is and that you could visually see where that would be on the graph. And so I will show you what the graph of this function looks like now. And there it is. As you can see, the red curves are approaching the horizontal asymptote of y equals 2. All right, let's do another example. Okay. So at this point, I would hope you guys realize that we're going to start by saying, okay, the limit as x approaches infinity of f of x is equal to the limit as x approaches infinity of the first two terms only. And if we reduce this, now something different is going to happen this time. X over x squared reduces to 1 over -4x. Okay? Now, what case does this fit? This is a different case. Both of the last examples that we did were case 2. But what case is this? Is this the case where I have a x in the denominator Or is it a case where I have just a number? Or is it a case where I have an x in the numerator? Well, the answer is I have the x in the denominator. And what does this tell me the limit of this type of function is at in positive infinity and at negative infinity? For both positive infinity and negative infinity, the limit is 0. And that means my horizontal asymptote is at 0. So for this function, since the x is on the bottom, the limit of this thing at infinity is going to be 0. And that's true whether we're dealing with a positive or a negative infinity. So instead of writing it twice, I'm just going to go through and change my infinities to plus or minus. Okay? And what that means is I have a horizontal asymptote at y equals 0. I'm going to abbreviate horizontal asymptote with HA there. And I'll go ahead and show you guys the graph. And there it is. It's kind of hard to see, but it comes up and it gets closer and closer to that y equals 0 there. All right. So that's another example. Let's take a look at another one. So why don't you guys pause the video here for about 3 minutes and see if you guys can find the end behavior of this function and find where its horizontal asymptote will be. Okay, here we go. So here's our setup. The limit of this function at infinity is equal to the limit of its first two terms on the top and bottom at infinity, which reduces to this, negative 4 over x at infinity. And once again, since we have an x in the denominator, the limit we're approaching is 0. And that means we have a horizontal asymptote at y equals 0. And if you guys want to see what the graph would look like for this function, there it is. Okay, let's do a third example. Okay, here we go. So once again, we have the limit as x approaches infinity of our function can be found by finding the limit as x approaches infinity of just the first two terms. And in this case, we end up with something interesting. We end up with x over 4. Well, I need to write my limit on there. Let me back up a little bit. Limit as x approaches infinity. If you reduce this fraction, you end up with x over 4. Now this time the x is in the numerator. Okay? Now that kind of fits case 3 here. In case 3, if you want to think of this as over 1, the x is in the numerator. Okay? Now in that case, you have a polynomial type of situation going on here. So we're going to use our polynomial chart. Okay? So what we're going to look at is we're going to look at the sign of the number. Is it positive or negative? And we're also going to look at the power and determine whether it's odd or even. Okay? So, and then after that, we're going to use our chart. Now, when I look at this thing, I see that there's no negatives. So that means we're dealing with a positive a. And also the power on my x is 1, which is odd. So we're looking at case 3. And in this particular case, we have a positive a and an odd n. So my arrows are going to look like this. It's going to go up on the right and down on the left. So what that means is my limit at the right is going to be infinity, but my limit at the left is going to be negative infinity. So for the one with the positive infinity, we're going to say it's infinity because it goes up on the right. But now I'm not going to write this whole thing again. It's not necessary because everything's the same except the end spot. At the end, what we found is that for where we move to the left, that's what this means. X approaches negative infinity means we're going to the left. It's going down on the left side, so therefore it's approaching negative infinity on the left. So positive infinity for x going to the right, negative infinity for x going to the left. And so this graph does not have a horizontal asymptote. When it goes up and down, up or down forever, it doesn't have like a little barrier that it's getting flattened up against, which is the horizontal asymptote. It just keeps going up. So on the right of my graph it goes up, and on the left of my graph it goes down. Let's see what the actual graph looks like. Okay, so my arrows are not touching the graph, but that's okay. Let me erase my arrows. As you guys can see, it's just going up. And over here it's just going down. It's not getting flat. It's just going to keep going up, 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 up. And over here she's going to go down, 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 down. So the limit at the right is positive infinity. The limit at the left is negative infinity. Okay? I'll throw another one of these examples at you here. Let's take a look at another one that's like that. All right. I'm going to make a little change here, though. I'm going to call that a 4. So let's go ahead and write that one down. All right, so for this one, the limit of my function as x approaches infinity is going to be equal to the limit of the first two terms at infinity. And then we reduce it, and that's going to give me x squared over 2. And now I get to use my chart to figure out what's going on the right. Well, now I want you guys to think. Positive A, even power. What should go over here? Think about it for a moment. Look at your chart, see if you can figure it out. Positive A, even power, well, it goes up on the left and on the right ends of the graph. So, since it goes up as I go to the right, that's what x approaching infinity means, then that means my y value is approaching infinity. As for the moving to the left, well, according to our chart, as we go to the left, it's also positive infinity. And so this graph on the left and right hand side is going to be going up on both ends. Let's see what it actually looks like. Oh, you know what? This graph isn't the correct graph because I changed the number, so you can ignore the graph. But since I changed the number, even though I can't show you what that graph would look like since I changed the number, both sides would be going up. That's the most I can show you at this point. All right, so I'm going to give you guys one more student practice to give that a try. Okay, there you guys go. Probably need about 3 minutes for that one. Give it a try and see if you can find out what the end behavior is. You should be able to tell me whether it's positive infinity, negative infinity, and should know which way the arrows are going. Okay, so here it is. After you apply all your limit stuff, you end up with x over negative 4. That's a negative fraction with an odd power, which, according to our chart, when you have a negative and an odd, it's down on the right and up on the left. So for my right-handed limit, it's negative infinity. And for my left-handed limit, it's positive infinity. So that's why up here we have negative infinity, because as I go to the right, the y value goes down. And as I go to the left, my y value goes up. And then we can take a look at the graph to verify that. As you can see, it's going down on the left side, and it's going up on the right side. Okay? Now at this point, since I'm not here, I really don't know how much class time you guys have left. But what I want to do is I want to share with you guys a shortcut. Now the shortcut only applies to cases 1 and 2. Case 3, unfortunately, it's nasty and it stays nasty. But cases 1 and 2 are pretty cool. So if you have time, or if you want, you can look at it at home tonight for homework if you guys don't get a chance to finish it in class today. I will show you guys a shortcut. So let's take a look at a shortcut here. It can save you a little bit of time and make life a lot easier. But I wanted to make sure you guys understood the concept before I gave you the shortcut. So let's take a look at the shortcut. Here we go. Okay. All right, so here's one of the shortcuts, okay? If the power on top is less than the power on the bottom, then the end behavior is 0. That's your horizontal asymptote, okay? So for example, if I gave you guys something, well, I'll give you guys an example in a minute. Let's just ignore that. Let me give you guys the other shortcut. There's two of them. If Okay, here's our second shortcut and our last shortcut. If the power on top is equal to the power on the bottom, so like when you take those first two terms, put them over there, and those two powers are the same, well, these get eliminated, don't they? And all you're left with is what coefficient was on the top and what coefficient was on the bottom, which would be a over b. And so that ends up being your horizontal asymptote. So there's your shortcut. Okay, so I want to show you guys a couple of examples where you can use the shortcut and maybe save yourself a little bit of time. Okay? All right. Notice in this case, the power on the bottom is 2, but there is no power on the top. So in this case, the power on the top is less than the power on the bottom. And if the power on the top is less than the power on the bottom, then the end behavior is 0, and that's what your horizontal asymptote would be. So we don't have to do any work. We can just say that whether you go to the left or right, the limit of this function at positive and negative infinity is 0, and that's where your horizontal asymptote is going to be. Okay? Here's another one. Find another. Same thing. I'm not going to write it this time, but as you guys can see, power on the top is less than the power on the bottom. Your horizontal asymptote is going to be at y equals 0. This is neither one of the cases I gave you. Notice the power on top is greater than the power on the bottom. The two shortcuts only apply if the power on the top is less or if the two powers are equal. So in this case, there's no shortcut for this one. You have to do it the long way. Let's look at another one. Notice for this example, the two powers are equal. They're both 3. And according to the shortcut I gave you here, if the power on the top is equal to the power on the bottom, then basically you can just take the coefficient from the top and put it over the coefficient of the bottom, and that gives you your horizontal asymptote. So for instance, the limit of this function, as we go to the left or right forever, is just going to be this coefficient on the top, which is 1, over this coefficient on the bottom, which is 2. So it's 1/2. And that's also what your horizontal asymptote would be. Okay? So it's a shortcut. Saves you a lot of time, makes it a lot easier. But once again, it only applies to the two situations I gave you. If you ever end up with a power that's greater on the top than the bottom, then you got to do it the way we've been doing it for the rest of the day. So this is an example of one that we have to do the long way because the power on top is greater than the power on the bottom. Here they're equal, so the answer would be 2. Negative 2, sorry. Here, the power on the top is less than the power on the bottom. The answer would be 0, and so on. Okay, so there's your shortcut. Definitely probably don't have any more time in class. I can see the time frame here has been 40 minutes. We usually stop around 32. So, I don't know, maybe you guys were checking this out on the at home or for homework or something. But there's your shortcut, and we'll see you guys tomorrow. You have your quiz, so be studying up for that. And this homework will be due. Actually, we're going to be studying for our quiz in class tomorrow. So bring this homework with you tomorrow. So anyway, see you then.